Tonight's speaker, Jim Butler, is a senior scientist in the geohydrology section of the Kansas Geological Survey at the University of Kansas. He holds a BS in geology from the College of William and Mary and MS and Ph.D. in applied hydrogeology from Stanford. His research interests include assessment of aquifers that support irrigated agriculture, well responses to natural and anthropogenic stimuli, and stream aquifer interactions. Jim was the 2020 recipient of the M. King Hubbard Award of the National Groundwater Association in recognition of his scientific contributions to groundwater hydrology. Welcome, Jim. I'm going to stop sharing so that you can start sharing.
Okay, well, let me get my screen. I'm going to turn off my video simply because I find that distracting. Let me share the screen here. Share screen. Should be a full screen slideshow now. Is that correct?
Yes, that's what we see. Thanks.
Okay, well, thanks a lot, Dave, for the introduction. As Dave said, I'm Jim Butler with the Kansas Geological Survey at the University of Kansas. For those of you who don't know the survey, we are a research and service unit of the University of Kansas. We have no regulatory or policy making function. Basically, our mission, when you cut to the chase, is to provide a sound scientific foundation for decision-making on natural resources issues within the state of Kansas. And obviously, one of our big natural resources is the water in our aquifers. And that's what I'm going to focus on tonight and just talk about some of the challenges that we face and some perhaps promising paths forwards we have. I'm going to start with just some basics on Kansas water resources. And so what I've got here is a figure of the average annual precipitation in the state of Kansas. And I should note that I have all these slides in both metric units and English units. But whenever I give a presentation in the state of Kansas, I go with English. So I decided for you guys in Minnesota, I would go with English units as well. So what you see here with the annual precipitation is a strong gradient as the precipitation decreases east to west across the state. So here in the southeast corner of the state, we get over 46 inches of rain, of precipitation a year. And then you go across the state here, we got it in 5-inch increments. And the far southwest corner of the state, we're under 18 inches per year. And so the western third to 40% of the state is basically in semi-arid conditions, but obviously it's quite a bit different on the eastern side. So that's the situation we have, that we face. And so now the question is, how much water do we use, and what is it used for? And so this next slide gets at this. So what we've got here is basically pies for every county in the state. And the size of the pie is an indication of the volume of annual water use. And the units here, acre feet. And so basically what you've got, that represents the volume of water ponded 1 foot deep over an acre. And so it's just a tad over, what is that, 326,000 gallons for 1 acre foot. So what we've got here is a tremendous difference, again, between the East and the West. And you can see in the East, there's a lot of municipal use. So the colors of the pie slices are based on the uses shown in the lower left there. And so in Kansas City, you've got municipal dominates. I'm in Douglas County in Lawrence, Kansas. by the way, which is the home of the noble and inspirational Jayhawk. What an incredible mascot. And you guys in the Big Ten, you're fooling around with gophers and whatever. Bad, it just doesn't have that same power as a Jayhawk. Just thought I'd throw that in. Notice this large gray area here in Douglas County. That's a hydropower plant. So that's a non-consumptive use of water there. As you go west, notice the dominance and the volume of annual irrigation. Because we're not getting much rainfall, agriculture is big out west. We've got to get the water to grow the crops. So irrigation. So where does that irrigation water come from? Well, here we've got the source of the water, and you can see in the eastern side of the state, mainly coming from surface water, streams, rivers, lakes, so on. But as you go west, semi-arid western Kansas there, groundwater is dominating. Now notice the gray area that underlies portions of western and south central Kansas. This is the High Plains Aquifer. And you can see we're drawing lots of water from the High Plains Aquifer in support of irrigated agriculture. So one other kind of introductory comment I wanted to make is about aquifers. Now, you've got a wide variety of aquifers. The High Plains Aquifer, which will be the focus here, we're actually focusing on a subcomponent of that, is basically, it's just a pile of sediment grains ranging from gravels down to silts and clays. And that space between the grains is where the water, the groundwater resides. And when that space, called a pore, is filled with water, it's considered saturated. And so the aquifer basically has a thickness of saturated material. So it's a water-saturated geologic unit, and it readily yields water to a well. And we've got this inset here on the right. You can see the grains. You've got the water table, which is on top of the aquifer. And you can see the grains filled with water, the spaces between the grains filled with water below the water table. And above that, you've got a mix of primarily air with some water. Now, the key point I wanted to make with this figure is these spaces between the grains are extremely small. So when groundwater moves in an aquifer like this is an unconsolidated aquifer. So these grains are not cemented together as in a rock, as in bedrock. This is an unconsolidated aquifer. As water moves through it, it moves very slowly because of all the friction involved that has to be overcome because of these very small spaces. So typically, under natural condition, groundwater moves very slowly, taking 1 to 3 decades to go a mile. Now, obviously, close to a pumping well, it'll pick up speed as the water converges on the pumping well. So when we think of an aquifer like this, think about local. It's the scale of interest is local. Some individual 15, 20 miles away is not affecting you. It's all about the situation in your immediate vicinity. Groundwater is moving slowly, and it's just, you're just not being impacted by great distances away for the most part. So we typically, when I talk to the irrigators out west in western Kansas, I talk about the old ad slogan for Las Vegas. What happens in Las Vegas stays in Vegas, or something like that. And that's similar when you think of groundwater. Think of that slogan, because it's hyper local is the scale of interest. So the question is, where are the aquifers in Kansas? And that's easily demonstrated by a map like this. This is a map of all the wells with active water rights for groundwater. And For domestic supply, you don't need a water right, although folks do get them, but you don't have to. But anything other than a domestic supply, you need to have a water right. And notice the clumps of water rights in western Kansas, south central Kansas here. This is the High Plains Aquifer. Now, you also have these sinuous bands that run through, for example, north central, and as I'm showing here, eastern Kansas. These are the aquifers that underlie the floodplains and our major river valleys. But our focus tonight is going to be on the High Plains Aquifer, this area with these clumps in western and south central Kansas. Now, the High Plains Aquifer is not isolated to Kansas. It extends over 8 states in the central US. It's one of the largest and most important regional aquifers in the world for all the agriculture production that it supports. Now, I'm going to focus on the portion of the aquifer in Kansas, which you're seeing in this inset, and I'm going to expand that in this slide. And the High Plains Aquifer is this yellowish material. You also see, I guess that's a brownish material here on the borders. This is similar geologic material, but with little groundwater. And I should note that the depositional material, the High Plains Aquifer is basically erosional debris carried east from the ancestral Rocky Mountains. So that's kind of alluvial in origin. So in Kansas, we subdivide the High Plains Aquifer into 3 components. In the western semi-arid third of the state, we have the Ogallala Aquifer, which will be the focus of mine tonight. In south central Kansas, we also have the Great Bend Prairie, and in the far eastern portion of the High Plains Aquifer in the state is the Equus Beds Aquifer. And the Equus Bed provides a significant amount of water to the city of Wichita's supply. So in this case, I think it's something like 30+% of the water pumped out of the Equus Beds goes for municipal use. Everything else in the Great Bend Prairie, the Ogallala, it's 95% of the water is used for irrigation. So our focus is going to be on the Ogallala Aquifer in the semi-arid western portion of the state of Kansas. Now, this aquifer has been heavily pumped for decades in support of irrigated agriculture. And that intensive use has come at a price in terms of aquifer conditions. And I wanted to give you one illustration of that price with this next slide. So this is a map of the percent change in aquifer thickness since pre-development, since the onset of widespread pumping for irrigated agriculture. And typically we think mid-1950s and earlier. Now on this map, the areas colored with blue are areas of aquifer increase since pre-development. Everything else is aquifer decrease. And I should note that the portion of the blues in the western, I'd say 50% of this map. So all this area, you can see by my cursor and down south of there, these are areas of very thin aquifer at pre-development from the get-go and are not of practical significance. But what I wanted to draw your attention to is the areas with the deepest reds. And these are areas where over 60% of the aquifer has been lost, has been depleted since the onset of widespread pumping for irrigated agriculture. And in those areas, and lots of these areas with this reddish color, continuation of business as usual is not going to end well. And so the question that I wanted to address tonight is to ask, what is the future of the Ogallala Aquifer in western Kansas? And are there some promising paths forward that we can chart to moderate this situation that you see here? But before doing so, wanted to talk about one of the issues, and that is this depletion of the aquifer has produced what I would call hydrologic collateral damage. And what I mean is the surface water resources of Western Kansas have been affected by the aquifer depletion. And I'm going to show this with this next slide. And this was put together by a colleague of mine, Sam Zipper, here at the Kansas Survey. And what we've got here is a map of the major perennial streams as of 1961. And a perennial stream is one that's always flowing. So the blues here were perennial in 61 and again in 2009. Now the reds are streams that were perennial in 61, but not in 2009. And notice this gray area, again, is the High Plains Aquifer. And notice how these red areas are basically all over the High Plains Aquifer. And what's happened here is these were originally groundwater fed rivers and streams. The water table, the elevation of the water table was above the elevation of water and stream. So water flowed from the aquifer into the stream. But now with all this depletion, we have dropped the water table way below the bottom of the streams. So we have basically reversed that gradient and essentially drained the streams. And I wanted to draw your attention to one of the major rivers in the state of Kansas, what we call the Arkansas River. Now, I just wanted to interject one note. Now, I understand that many of you probably follow along with this Arkansas, this pronunciation promulgated by the state that calls itself Arkansas. We've got it right in Kansas, and I'd be happy to take questions on the historical roots of that pronunciation. But I just wanted to notice you to know that we call it the Arkansas River, as would be expected from the spelling. Now, the Arkansas River comes actually out of the Rockies, flows across eastern Colorado, comes into the state of Kansas, and goes to about the point I've marked A here. And that's just downstream of the only surface water irrigation area in the High Plains that was set up in the 1880s and has priority over virtually all other uses on the river. They divert significant quantities, and sometimes they divert the entire river into their irrigation system there. For those of you who know Kansas, this is just west of the city of Garden City. And anything that's left over quickly drains out the bottom of the river. So from point A to B there in this figure, it's about probably a little over 150 river miles. And there has been no flow over that stretch in the last, 22 years. And a typical view of the channel around the point labeled B, where we've had a research site since 2002, is shown here. And this is just a dry riverbed. And in this area, the riparian zone is still doing reasonably well. The water table is relatively close to the surface, so these trees can send their roots down to the water table. These are phreatophytes, waters that use groundwater for their water supply. But this river, which was never a real deep river, it was wide and shallow, it's no longer flowing in this area. Now, I don't want to make light of this disheartening image you're seeing here, but I did want to note that the Arkansas River is one of 3 rivers in the state of Kansas that is legally classified as navigable. And obviously, that the definition of navigable has changed, as you can see from these ruts here on the right side. That is now via ATV, unfortunately. But this is the situation that has been produced by groundwater depletion. This additional hydrologic collateral damage that I mentioned earlier. So this is a situation we have currently. We've got very significant depletion in many areas in the Ogallala Aquifer in western Kansas, and we've got our streams and our riparian systems have been heavily impacted. So the question is, how did we get here? And so I wanted to take a few minutes just to give you a quick overview of water resources management in Kansas. And as many of you know, in the United States, the water management is the state responsibility. And in Kansas, we have the lead agency for management of both surface and groundwaters is the Division of Water Resources of the Kansas Department of Agriculture. And they have a chief engineer who's basically the water guru. He makes all the calls and concerning who can use the water and this sort of thing. And we have water rights that I'll mention here in a minute that his office is the decider on as well. Now, I should note that Kansas is the only state in the American West that has their water resources agency in a Department of Agriculture. So just something to keep in mind. But one good aspect of this situation in Kansas is that we manage surface and groundwaters as an integrated whole. It's in some states, they've got one agency handling groundwater, one agency handling surface water, and that just doesn't make sense because in nature, it's an integrated system. So this Division of Water Resources is located in eastern Kansas, and that caused some concern in the High Plains Aquifer. They didn't think they were being represented well. And so back in the mid-70s, there was a series of 5 groundwater management districts were set up in the state, all of them overlying portions of the High Plains Aquifer. And I've got them shown here. These allow some local input into decisions about water resources management. These management districts can have their own, come up with their own management initiatives. And as long as those are fit within the framework of Kansas water law and are approved by the chief engineer, they can move forward with them. Now, they have an elected board, but the general populace does not vote here. The folks who vote are folks who either own 40 or more continuous rural acres or have a water right of 1 acre-foot or more. And again, 1 acre-foot's about 326,000 gallons. And they have taxing authority for their members, not for the general populace or not the irrigation community. So you've got these groundwater management districts. I wanted to bring that to your attention. Also, I wanted to talk just briefly about groundwater-based water rights in Kansas. In Kansas, we use the prior appropriation doctrine for water rights. And this basically is seniority rules. And it was set up back in, I guess it was 1945 with the Water Appropriation Act of Kansas. And people could then apply for water rights. and of the first in time, first in right, as I show here. And the more junior folks cannot impair more senior users. Now, as you can see by this aerial view here of southwestern Kansas, I should note the majority of these circles, these are center pivot circles, the majority of them have a diameter of, that would be a half-mile diameter. The larger ones are a mile in diameter. And you can see the proximity, the close proximity of all these central pivots would lead to some impairment, would likely lead to some impairment. And if a senior user complains, then you can have water rights administration, and the junior users could be affected, would have to reduce their water right, and in some cases just stop irrigating. Now, this system of prior appropriation was considered to be a check on depletion, but the reality shows that it hasn't worked. And why is that so? Well, I think there's three reasons for that. One, administratively, in 1957, the legislature changed the definition, they weakened the definition of impairment. And so now one had to prove that there was it had a financial impact. That can be difficult to prove. They also set it up so regional declines are not considered impairment. Because I guess they figured they couldn't figure out who was causing the declines. But so there's some legislative moves that made it more difficult to go forward with impairment claims. However, I think the two major reasons are, first, claiming an impairment in a groundwater situation, where again, it's hyper local, means that you're saying your neighbor is impairing you and you want him shut down. But you may have known him since you were a toddler. And so it's a difficult situation. Unlike surface water, which is routinely used in Kansas, the prior appropriation doctrine routinely applied. It could be some guy 15 or 20 miles upriver from you who's impairing you. Shut him down. It's no big deal. But here, it's your neighbor. It's not considered an impairment complaint in Western Kansas is not considered a neighborly act. And so in my career, there have been very, very few claims. And most recently, back about 15 years ago, or I guess it was 12 years ago, there was a claim that senior water user was being impaired. Basically, the community turned on him and tried to bankrupt him as a result, because there's a heck of a lot more junior users than senior users. So he eventually had to back down. And so no one has moved forward with impairment claims. Another reason is the average irrigator has a portfolio of water rights of different seniority. And so the fear is, if you decide to say someone's impairing your use, that there could just be like a domino effect and you could end up shutting yourself down in the process. So that's also restricted people moving forward with impairment claims. Now, the chief engineer has the legal authority to do so, but I think political expediencies have made it difficult. And so there have been no impairment claims in the High Plains Aquifer that have been initiated by the chief engineer. So this is our situation, and we're looking at these conditions you see in the upper half of this slide, and we want to ask ourselves, what can we do now? What can we do to try to ameliorate this situation? And frankly, right now, there's not much we can do to get our streams flowing again. I just don't think that's in the cards for any time soon. However, we can move forward with measures to reduce the rate of decline, and in some areas stabilize the water levels in the High Plains Aquifer. And I'd like to talk about that in the next section of this. I'm going to take a brief break and to get some water. Let me just take a minute here. If someone has a pressing question, I can take it now.
Okay, there is the question from Patrick. Okay, I'll bite. As a major history nerd, I'd love to hear more about the pronunciation of Arkansas. But we can probably leave that one to the end.
Yeah, let's leave that to the end. That's an interesting story. I'd be happy to talk about that. Okay, so if nothing else, let me launch into what can we do to moderate the rate of water level declines in the High Plains Aquifer, in the Ogallala Aquifer in western Kansas. Well, we've got three options. I'm going to go through them quickly here. One, replace groundwater with surface water. It's obvious. The problem is there's no surface water to be had, no excess surface water to be had in western Kansas. So now you're talking about long distance water transfers. And well, in Kansas, of course, in southwest Kansas, they think that's a great idea in quarters there. And they've proposed, since the early 80s, there's been this idea we're going to have this aqueduct. We're going to take water from the Missouri, far northeastern corner of the state, and send it. And you can read the statistics there. And I should note that 1.6 million acre feet per year comes out to 521 trillion gallons of water that they're going to send up 1,600 feet and 360 miles. And you can see where it ends here is not where you need to use it. They're going to have to distribute it from there. This is going to be a huge project that is just not going to be cost effective to grow grain. And there was an article in the Wall Street Journal last March that talked about this, and one of the major water lawyers in the state said it will never happen. Now, I give briefings to the state legislature, and when this comes up, the Kansas Geological Survey doesn't take any position on such projects, but I can say that regardless of one's view on the merits of the project, we can all agree on one key point, and that is it's not happening anytime soon. And I'll look out at the audience and define soon as the lifespan of like 80% of the people in the room. So this is not what is going to get us moving forward. So the second idea, possibility, is having subsidies for water efficient equipment. And this sounds very intuitively appealing, but the results have shown in Kansas, we've done analyses of this issue using data from 96 to the present in all areas of the High Plains Aquifer, and irrigation efficiency improvements have not led to water conservation in the High Plains Aquifer in Kansas, and this is true across the world. Efficiency improvements do not lead to less use. And this is consistent with Jevons paradox of natural resources economics, that this guy in the UK, Jevons, came up with this regarding coal back in the 1860s. Just improving efficiency leads to more use. Now in Kansas, there's a cap on the use, but based on your water right, but you can certainly use the excess water that you save from irrigation efficiency to grow more water-thirsty crops, or expand irrigated acres, et cetera. So unless the irrigation efficiency improvements, these subsidies, are tied to a legally binding agreement to reduce water use, you're not saving any water through the adoption of irrigation efficiency measures. So that leaves us with one option left, and that's pumping reductions with modifications of agricultural practices. This is a promising option, and this is what I wanted to focus on for the remainder of this presentation. And so in Kansas, the legislation realized back in 2011 and 12 that we had serious problems in Western Kansas. And so in 2012, they passed some new measures to enhance prospects for pumping reductions. And this was the Local Enhanced Management Area, or LEMA program. And the basic idea here is it's a combination, it's a hybrid of a grassroots generated plan by irrigators that is then supported by regulatory oversight. So a group of irrigators get together and say, hey, we want to reduce water use by a certain percentage so that we can extend the aquifer lifespan so our kids and grandkids can enjoy the same lifestyle we have. And if the majority of the folks in the area say, let's do it, then everybody in that geographical area has to follow suit. And the state regulatory agency comes in to make sure everyone's following the agreed upon rules. So this hybrid model, grassroots with regulatory oversight, has some real potential. And in 2015, a smaller version of this, I won't go into it, but it's a similar idea. And all I wanted to mention just in passing that you have to have this regulatory oversight. You can trust your neighbors, but when you're reducing water use and the potential impact on your bottom line, you want to make sure that everyone's following the agreed upon rules. So that trust but verify idea that harkens back to Reagan and his arms control negotiations with Gorbachev. So what I thought I'd do is look at this pumping reduction idea and go in to one of these local enhanced management areas that has been established. And I'm going to go in and look at the area that was established in 2013. And it's what we call the Sheridan 6 Local Enhanced Management Area, or the Sheridan 6 LEMA, 99 square miles. And their idea was to reduce pumping by 20%. This would be the annual pumping. And they have a period of like a decade prior to the establishment of the area that they use to set their average pumping, and they want to reduce it 20% from that. And on this map, you can see some later local enhanced management areas that have been set up in 2018, and then just recently this year, we have another one going in this 4-county LEMA you see listed there. So the question is, let's look at this one that's been going since 2013. So they've been operating for a decade. So how have they done? That's what the question I wanted to get at here. So we came up with some, using the principle of parsimony, just the basic key requirements for successful groundwater conservation area, and using these to assess how this area has done. And obviously, the first key requirement is groundwater pumping must be reduced. And how do you assess that? Well, you don't need any real sophisticated analysis here because we have the data. And so my colleagues and I came up with this very simple plotting approach. And what I've got here on the x-axis is annual precipitation in inches, and PRISM is just a data set from which the annual precipitation data were drawn. And on the y-axis, you've got annual groundwater use, and this is in units of 1,000 acre feet. So just for your information, 30,000 acre feet, which would be right here, is equivalent to about 10 billion gallons of water. So that's how much this 99 square area, that's how much they can use in a year. Got two sets of data here. The blues are prior to the establishment of this area, this LEMA. And we've set, just did a quick linear regression there through the data, 95% confidence intervals. The reds are data after the establishment of the LEMA. Notice that you've got that clear break there. That's this downward move in the LEMA data. The offset is clear. For the similar climatic conditions or a similar annual precipitation, you can show they've reduced pumping by about 31%. Now, notice a couple other aspects of this. Notice how tight the linear regression is for the Lima period compared to the pre-Lima period, both of them 95% confidence intervals. And that's because they're now using this irrigation efficiency technology. So it can be used to get you from your previous pumping to this new level. And that's what I was talking about. If you tie that to a binding agreement to reduce water use, you can achieve a lot. And notice that the slopes are different. The Lima slope is steeper than the pre-Lima period. And talking with the irrigators out there, they told me that once they had these soil moisture sensors in place, that they found that they were using way too much water during normal to wet periods. And so that's been a major area where they've been able to reduce water use. So it's clear, and I should note there's 199 pumping wells that are being used for the calculating annual groundwater use. And it's clear they have been able to reduce water use. So groundwater pumping must be reduced is a necessary condition for successful groundwater conservation area, but it's not a sufficient condition, because why are you reducing groundwater pumping? Because you want to reduce the groundwater decline rate, the water level decline rate. So how have they done in that score? Same idea, simple data plot, annual precipitation there on the X, and now you've got average annual water level change here on the Y with the negative numbers, meaning water level declines, positive water level increases. And again, you see this offset. In this case, the water level declines are less than those during the Lima period are less than in the pre-Lima period. And it comes out for similar climatic conditions, you're reducing water level decline rate approximately 62%. So more noise in these plots because you have 7 to 11 wells are being used to calculate the average annual water level change here. Some of the wells are very tricky to measure, and we now go in and measure them repeatedly during our annual measurement campaign to see if we can get better data. But it's clear, again, that offset. So they have been able to reduce water level decline rates as well as the groundwater pumping. So they've done what hydrologically what is required, but that is still not a sufficient condition for successful groundwater conservation area, because if this is going to work, it must be economically viable. And I'm pleased to report that ag economists working with the producers have found that they are making just as much money now as they were prior to the reductions in groundwater use. Although the yields, crop yields are slightly down because they're not using as much water, they're not pumping as much water, so they're saving a lot of money in terms of energy cost as well. So they've been able to meet all 3 key requirements that we set for a successful groundwater conservation area, and their success has influenced the others in the area, as you can see by the establishment of 3 other Limas after this one was established, and shown to the area, to folks, that they can make money and also reduce the water level decline rates. So this is an example, a successful example of what can be done to extend the aquifer lifespan. Unfortunately, not all of these Limas that are now in existence have as steep of declines of water level pumping, groundwater pumping declines as we would like. But it's a start, and so we're mildly optimistic. So I'm going to return to the question that I asked about a third of the way through this talk. is what is the future of the Ogallala Aquifer in Western Kansas? And the answer is it depends. It depends on what the irrigation community in Western Kansas decides to do. Now, clearly, the hour is late, as shown by all these red areas. Continuation of business as usual, as I said earlier, is not going to end well for groundwater-based irrigation in many areas of Western Kansas. But all is not lost. This local enhanced management area program, plus the other program I mentioned, these water conservation areas, if these could be spread across the aquifer in Western Kansas with pumping reductions on the order of 20 to 25%, we could make significant strides forward for extending the lifespan of the aquifer, and maybe in certain areas being able to stabilize the water levels for decades, and then hope that crop genetics, different crop mixes, etc., could help us fend off the impacts of climate change coming down the road. So there is potential. So I am guardedly optimistic. However, there's a window, we have a window of time in which we can make a significant impact on this issue. But this window of opportunity is not going to be open forever. And so my colleagues and I try to get the word out that there's the potential of these local enhanced management areas, et cetera, that can make a big difference and help support irrigated agriculture in Western Kansas for decades to come, and the rural communities that depend on it. So with that, I'm trying to keep it under an hour, so I'm getting close to that. So I'd be happy to take any questions that folks might have. And let me just very quickly end with this slide that just acknowledge funding sources for our work, funded by both state sources as well as competitive federal programs. And for further information, I've listed 3 publications here. The first and third can be gotten directly from the Kansas Geological Survey website, or you can email me and I can send them out to you. The second is a paper that I wrote for a general audience, and that was for a theological journal that had their first ever special issue on water, and asked me to write on groundwater, some groundwater issues. So I can send that on to any interested as well. And so with that, I'll bring this to a close, and I'd be happy to take any questions that folks might have.
Okay, this is Dave. I'm gonna, first of all, anything you send, you can send to Steve and me, and we can get it to the rest of our organization.
Okay.
I'll have my own question here first. How deep are these aquifers? And really, the question is, how deep are these wells? So, from how many feet up are they pumping water?
Yeah, I mean, it depends on where you are in Western Kansas, but in general, think 150 to over 300 feet in terms of the depth to the water table. So you could see that if you're pumping large quantities, you're lifting a lot, it's expensive to pump the water.
It sounds that way because I mean we're talking millions of gallons.
Yeah,
It doesn't, yeah, and you're lifting against gravity.
water's heavy.
Yes. There's a question in the Q&A here from Dave Peters. Does the landscape subside when the aquifer gets depleted? And how does that affect the farmland?
Well, we have had very, very little indication of groundwater, of surface subsidence. This is, in the Central Valley of California, this is a huge issue because they have these thick clay units that dewater and then they just collapse on themselves. The porosity goes to very small amounts once they get to water. We don't have that situation in Western Kansas, so we have minimal amounts of subsidence. Now, maybe in the
Okay.
future, maybe things will change, but as of this point, 60-some years into the depletion, where it's not well, 65 years, we haven't seen that.
So looking at your original diagram, the water is being taken out of the little gaps between but it's not, they're not packing together because of that.
Right. Yeah, because remember and you've got hundreds, depending on where you are, maybe 150 to, as I said earlier, to 300 feet of sediments above you. That's a heavy weight that's been imposed on it. So they're not compacting further.
Okay, I'm going to ask my own question again. So the aquifer gets replenished in some fashion. Obviously, it's being drawn down way faster than replenished, but it seems to me if you reduce by 20 to 25%, that's probably not enough to keep up with replenishment. Is that correct? But it pushes the problem out.
Yeah, I mean, that is correct. In most areas in Western Kansas, that is correct. They would have to cut it down to maybe 35, 40%. And that could stabilize the water level for, I would say, a few decades. But further out than that, I think it's difficult to say. We just don't know how, that climate change is going to impact us.
Okay. There's two kind of related questions here. One's in the chat. By the way, it's best if you put your questions in Q&A. I'm going to ask both questions and I'll let you. So the one from Mike says, are different crops being grown for the Lima groundwater depletion reductions? And there's a question from an anonymous. How much of the irrigated crops go to feed livestock? Climate scientists suggest we eat less meat. Could Kansas farmers switch so that they're growing crops for plant-based diets? So I think those are kind of related.
Yeah, I mean, as of now, the livestock industry is big in Western Kansas, and they are consumers of they like corn, but I think there could be some movement away from corn into sorghum and some other crops that are less water needy. So there is the potential for that to occur. Now in that Sheridan 6 Lima, they reduced the irrigated corn acreage a small amount, but it's still primarily corn. But they switched around how they did it. Their major contribution there was putting in the soil moisture sensors and related kind of precision agriculture technology, so that they could really get an understanding of when the plants needed water and when they did not. And they realized that they didn't have a good understanding of that previously. So they've been able to make some significant gains that way. But I think eventually crop mixes are going to have to be varied. And I think there's a willingness to move forward. I mean, the irrigation community the irrigation community in Western Kansas is, I mean, if you're a successful irrigator out there, you're highly adaptable and resourceful. And I think if they are presented with challenges, they'll rise to the occasion. I have a good friend of mine who's been irrigating for Well, his family's been on the land since the 1870s in far western Kansas. And he once told me, just tell us what we have to do and we'll make it work. And that's not really, the Kansas Geological Survey, that's not our role. But I think it's not going to be paint by the number agriculture, but I think they can move forward. And the one questioner about plant-based diets, that's not probably very popular right now, but who knows what the future might hold.
Okay, thank you. Here's a question from Dale. Are there no lakes in Kansas?
Sure, we got lakes. We have reservoirs and lakes in the eastern half of the state. There are a few reservoirs in western Kansas. They're not necessarily doing real well. There are county lakes in portions of western Kansas. One of them in west central Kansas is actually fed by the Ogallala Aquifer. It's just coming out. It's just flows into the lake because of the lake's elevation, and so it's below the water table in the aquifer. But for the most part, the lakes in western Kansas are filled by pumping the Ogallala Aquifer. So they're lakes, but that's not it's not a common feature. They do have farm ponds. The farmers will put dams on the streams in their area, the gullies, etc., and have small little farm ponds, which can be sources of recharge. The basic problem here, as you mentioned earlier, is the amount of water recharging is less than the amount being removed. Back in the 60s and through the mid 70s, the Division of Water Resources gave out way too many water rights. So there's just they over allocated the aquifer. They gave out more water rights than the aquifer can sustain.
Okay.
And I don't know if I
Question.
answered your question or not. If I went off, I'm not sure if I got to it. So feel free to follow up if I didn't get to it.
I think you got it, but okay. But I'll let Dale put more question in if he has more. Right now from Mary Helen, have any farmers tried using ground level drip irrigation tubes rather than the tall sprayers to reduce evaporation loss of the water used in irrigation?
Sure. That's they'll do what that's called mobile drip. So they basically take the central pivot and attach tubing, perforated tubing that they drag along the surface. And that's catching on more in western Kansas. Now you've also can have just the underground drip irrigation lines put in, but there are problems with rodents chewing out this, and that's not a real popular approach now, simply because of the damage due to rodents. But these perforated tubes that just drag along the surface are considered a reasonable approach, and those are used.
Okay, thank you. Joe Newberg asked, how much north to south flow is in the aquifer, and how much of an effect is this?
The major flow in the aquifer is west to east, because the elevation in Kansas, by the border with Colorado, it'll be like 4,000 feet. You get to where I am, and it's well under 1,000 feet, 600 or something like that. So there's a west to east decrease in elevation, and the groundwater flows basically along that west to east. I mean, there is some areas, some north to south flow induced by pumping. If you've got a concentrated area where you've drawn down the water levels in the aquifer, you basically create this cone of depression in the water table, then water can flow in from all directions into that. But north to south flow is not, regionally, that's not a big deal. It's the west to east flow.
And based on what you said earlier, that flow, regardless, is quite slow.
Yes, yes. Now, in other types of aquifers, like a limestone aquifer where you can have, that's what they call karst conditions. You get dissolution of the limestone. You can have these channels. Water can zip through that real fast, but that's not what we're dealing with in the High Plains Aquifer, the Ogallala Aquifer in western Kansas.
We have quite a bit of karst in Minnesota, so we're familiar with limestone caves, especially southeastern Minnesota.
Yes. You can go swimming in those aquifers. You cannot go swimming in the Ogallala Aquifer. Just wanted to emphasize that.
Okay, next question is from Patrick. If Lima is upscaled, could that legal restriction create better conservation conditions for more efficient irrigation techniques?
Well, what you want to do with the Lima is you want to have them spread across the state, but you don't necessarily want to have these huge kind of big areas under Lima, because what kind of sociologists have found is that if you keep the area relatively small, so the aquifer conditions are relatively homogeneous and the producer attitudes are relatively homogeneous, you have your best chance of getting buy-in from the community to reduce water use. As you get larger, you've got people, you have a lot of heterogeneity, both in aquifer conditions and in producer attitudes, because some folks have wells that can pump 1,000 gallons a minute, say, where another guy's pumping 22 or something like that. That doesn't lead to very good community agreement on how much pumping should be reduced. So keep them relatively small, but then just distribute them across the aquifer. I think there's that is the way forward. That is the promising path forward.
I understand what you said, but when I think back to the map I saw, look like some of the other ones were quite large. I mean, the one you showed is relatively small, but weren't some of the other ones quite a bit bigger?
Yeah, and they haven't been very successful.
Okay.
There's two of them on that map that are, both of them are relatively small. They have done about the same. Both of them have made very impressive gains. The other areas, they, again, because you have these heterogeneity and aquifer conditions, producer attitudes, they just couldn't get agreement to do much of anything. So it's, some have accused one of the Limas as kind of blue washing. Now, I think they were just trying to get folks into the Lima framework, and over time will reduce pumping more. But time is of the essence here, so you don't want to string it out too long, or it's going to be a little, too late to really make a difference.
Okay, I'm asking these questions not necessarily in the order they came in. This one's from Zenobia. Are farmers starting to get with the program with water reduction of water usage?
Yeah, I think there's a growing recognition that you can't just go with a status quo. It's not going to end well, as I said in the presentation. And what we've been able to do, and I didn't talk about this in the presentation, is at the Kansas survey, my colleagues and I have developed theoretically strong methods that enable us to be able to go to irrigators, different areas. They say they want to reduce water use by a certain percent. We're able to tell them with good reliability what the impact on the decline rate, or the water level decline rate, will be if they reduce water level that degree. So we do a lot of presentations in Western Kansas, particularly one of my colleagues, Brownie Wilson, does a lot of presentations where he shows to the irrigation community what can be done if you reduce water use by a certain amount. So I think folks are, they recognize that there's a need for that, but I mean, it's a risk. They see it as a risk to move forward with pumping reductions. How's that going to impact their bottom line? Even though these guys in the Sheridan 6 Lima have shown that they're still making just as much money as before, gosh, will that work with me? I've got different soils or whatever. So there's some inertia here that just over time we're hoping to be able to reduce and move forward.
Okay. Question, you showed a photo of a river that no longer flows. When it rains, does the water go directly in ground? Or does it flow a short distance, I guess, or no? And then also says, if it flows, does anyone use beavers to build dams?
Well, when I first started working at that site that I showed in that figure, there was a huge beaver dam there. And I had never seen the impact of beavers before. I mean, it's incredible what the beavers can do in a short period of time. They had built up this nice dam, and I think they were in good shape. Then there was a major rainstorm in a tributary just upstream of where I showed that photo, and that came down. The water came down and washed out that dam, and that was kind of the end of it. The river hasn't flowed much at all since then. I mean, they'll have a little bit of trickle coming through, but yeah, the beavers are no longer to be found in that area, unfortunately.
Okay. One of the earlier slides showed some aquifers that are filled a little. I think that's the blue areas on your map. Why?
Well, those are areas where the aquifer has increased. Now, in the western half of that map, those increases are minimal. It's just that at the start, whenever they took the initial measurements of conditions there, it's increased a bit since then, but it hasn't been anything significant. So say the aquifer at that point is 10 feet thick, and now maybe it's 11 feet thick. But still, it's not going to be supporting any sort of water supply. So now as you go further east, there were some blue areas in south central Kansas where those are areas, they get a lot more rainfall in those areas. And so they've been able to stay pretty close to stable conditions in those areas.
Okay. This question is 2022 appeared to be an outlier on your graph that showed reduced usage year by year, but 2022 seemed to be higher.
So I'll go back a few slides and let's see, which graph is he referring to? Maybe, or he or she referring to? Yeah, 2022. I assume this is the plot. This is there was a major drought in 2022, and they had a little trouble, and with those conditions. So they pumped more, and so it's relatively more than they've pumped in other years, as you can see. But that's due to one of them, the major droughts over the last 30, 40 years.
Okay, another question from Mary Helen. How much human population growth has there been in the Ogallala aquifer area? And how does it compare to aquifer depletion rates?
Well, there's no question that many of the rural communities are being hollowed out as the aquifer depletion increases. There have been areas in west central Kansas where they've lost the ability to go with irrigated agriculture. They've had to go with dry land, and that's had an impact on the communities. I mean, you can really see this further south in Texas. Some of the areas in the panhandle of the Texas have been severely impacted, some of the communities. But and yeah, I mean, that's a real problem. Outside of a few kind of economic centers, Garden City, for example, in southwest Kansas has seen some growth, but outside of that, maybe Dodge City, very, very little growth. In the population in most of those areas is diminishing, and it's aging, so it's an older population now. As many of the young people, they just don't see the opportunities that they would like in their home communities, so they've moved on.
And I'm guessing these populations were quite small to start with, anyway, right? I mean, it's quite rural.
Yeah, it's quite rural. I mean, you have some counties where the population is 2,000, so it's small populations.
Okay, the last question right now is the one that that Patrick put in early on. Okay, I'll bite. As a major history nerd, I'd love to hear more about the pronunciation of Arkansas versus Arkansas.
Well, I'm sure he recognizes that when you look at the word, that it's Arkansas would be the natural pronunciation. The problem here is when the state that calls itself Arkansas came into the Union, they had two senators, as all states do, but the two senators could not agree on how to pronounce the state's name or how to spell it. So you had one senator who went with the Arkansas spelling, and I mean the Arkansas pronunciation and the spelling that it currently has. The other senator ended it up, the word ended with SAW, and he went with Arkansas. So the state legislature they were embarrassed by this situation because each of them insisted on being introduced in DC with their spelling and pronunciation. So the state legislature did a deal. They turned to one senator and said, we'll take your spelling. They turned to the other and said, we'll take your pronunciation. And that's how the Arkansas pronunciation came to be. Well, let's face it, in Kansas, we could care less about some pronunciation by legislative edict by some state legislature in a state that has such lofty ambitions that it calls its state capital Little Rock. I mean, come on, at least moderate size rock. Come on, right?
Well, I don't see any more questions, and I think that was a great one to end on.
Say, Jim, this is Steve Erickson here tonight. Sorry I couldn't get on earlier. Thank you for joining us. It's been a very good talk. Excellent discussion and such. I have one question based on, now Minnesota, we have a lot of aquifers up here. What would you recommend us to be paying attention to right now to prevent ourselves from getting into that situation? What is something that you've learned that you could transfer up north here? What's your suggestion?
Well, the key advantage that we have in Kansas is we have all of the non-domestic pumping wells have totalizing flow meters. And the irrigators are required to report those amounts annually. It's subject to regulatory verification. The Division of Water Resources personnel have the legal authority to come onto an irrigator's land and clamp an ultrasonic flow meter right next to the irrigator's flow meter while the pump is going on and you have to be within 6% of the value for the calibrated flow meter, and that's because that's the manufacturer spec for that particular totalizing flow meter, and there's a requirement it be by a certain company, this sort of thing. So that enables us to move forward because we know how much is being pumped. And this is a problem with other states. I don't know if how Minnesota handles it, but we have 99+% of our high capacity pumping wells, of other non-domestic pumping wells in the High Plains Aquifer have totalizing flow meters. The US average is probably 30-some%. I don't know what Minnesota's is, but I would say if you want to manage a resource, you need to understand how much is being used. And so that, for me, is a key element, is to see if you can keep track of how much water is being used. Now, there's various ways to do it, but ET, remote sensing, all this jazz, utility records, but the easiest way is just to monitor it and have the state regulatory agency check, because you've got to have that trust, that verify deal. So that's, Steve, that's what I would say first. I mean, that's our advantage in Kansas. We also have a great water level measurement program, both annual, once-a-year measurements that has been going on for decades. We also have a network of continuous water level measurement wells where you have a pressure transducer down in the well measuring water levels every hour. We had to take that on because the USGS pulled back from a lot of their groundwater monitoring because of they decided to focus on areas for climate change impacts. And so those are areas that are not affected by anthropogenic activities. So we've had to step in and do that. So I think it's the data that I would focus on, because then you can see where you've got problems and begin to take measures to address them. Does that make sense?
Thank you. Yes, it does. That makes a lot of sense. I know that there is a certain amount of monitoring going on, but they've got a lot of domestic wells. By the way, and then make sure everybody understands, a domestic well you're talking about, I've got a pump out back that gives me my sink and my toilet, my shower, the water that I need, as opposed to I'm, manufacturing something or that. Is that correct?
Right.
Yeah. Okay. Yeah, that's a very, very interesting. We get a lot of water discussions up here. Every once in a while, somebody will talk about tapping into Lake Superior and pumping it to Arizona, which we think is like, really? But we did have one that broke last year where a company was going to pump water out of one of the aquifers, and I either bottle it or tank it to Arizona. And the DNR, Minnesota Department of Natural Resources, put the kibosh on that in a hurry. But that's still something that's discussed. Minnesota is blessed with a lot of aquifers, a lot of good water up here, with the lakes and the rivers and such. But there's, as we say, you don't want to get into the situation where, oh, by the way, we should have done this 50 years ago. So that was the question. So what you're saying is the data is the really critical element of the story. Very good.
Yeah.
Do we have any other questions there, Dave?
I don't see any other questions either in chat or in the Q&A.
Jim, I want to thank you very much for taking it on. And again, it's easier to say it was a computer problem as opposed to a computer operator problem, but that's what I had a little bit earlier. I didn't get a chance to chat with you. Thank you very much for your talk tonight. And anybody else has anything? Otherwise, I think we can wrap her up for the night.
Okay. Well, I'll go home and have some dinner. So thanks for having me.
Thank you for coming on board. Have a good day.
Okay. Take care.
Good night. All right. Have a good night, everybody.